Dear students, I welcome you for the today's lecture related to the thermal insulation and the critical radius of insulation. Now, the insulation, that is one of the important parts in the heat transfer to prevent the heat losses going to the atmosphere. So it becomes effective or important from the perspective of the cost as well as the insulation thickness. Two aspects. One is related to the cost of insulation, and second, that is related to the how much that thickness layer has to be provided. That is the critical layer of insulation. Now, in addition to that, we are going to discuss the different types of insulation, what are their properties, and why selection of the insulation. The insulation is necessary to prevent the excessive flow of costly heat to the surrounding from the process equipment or the piping system. That is the basic purpose why we provide the insulation, to prevent the excessive flow of heat going to the surrounding. So proper selection of insulating material that reduces this cost. Then there are two types of the insulations, that is one is cold insulation and second is the hot insulation. Now cold insulation, that is up to 0 degree Celsius, then ultra cold 100 Kelvin to 273 Kelvin, and for cryogenics, that is below 100 Kelvin. Then hot insulations is more common in the process plant, because generally it's your hot pipes, the temperature requirement is there for the process. Only in the cryogenic industries or certain food product industries where you require to maintain the low temperature, there the cold insulations that can be provided. Here the insulating material prevents the heat transfer from the process unit, which is at a higher temperature, to the surrounding, and insulate acts as a barrier and prevent the heat flow. Then what are the different insulating materials? Generally, the hot insulating materials are the asbestos laminates or asbestos fibers, then cellular glass and silica, cement made from mineral wool, water mix, then diatomaceous earth, then glass fibers, magnesia mineral cork, mineral wool, then expanded polystyrene and expanded polyurethanes, then reflective sheets and foils, that is nothing but the cladding. This expanded polystyrene and expanded polyurethane, that is used in case of our refrigeration system, that is below 0 degree Celsius. The rest are for higher temperatures, and the cladding that is to be provided over this insulation so that it is fixed and rigid. These are insulating materials common in process industries and are suitable for the environmental temperature ranges from 30 to 65 degrees Celsius and moderate temperature ranges from 65 to 300 degrees Celsius and 700 degrees Celsius. Then what about the higher temperature range, that is more than say 700 degrees Celsius? The refractive bricks made from the alumina silica or silica magnesite, chrome, silicon carbide, then fused alumina, etc. are used as the insulating material for higher temperature ranges above 700 degrees Celsius. That means in case of furnaces, you require the higher temperature where these refractive bricks which can sustain the higher temperature. There you require certain metals and minerals. That is what is the requirement to sustain it at a higher temperature. So we use the alumina silicate or silica magnesiate, chromium, silicon carbide, that is fused alumina, they will be used. Then what must be the desired properties of these insulating materials? They should have the lowest thermal conductivities. That is the one of the most important thing. They should be minimum thermal conductivity. Then and only then they are going to prevent the heat flow. Heat will not be passed. Then inflammable in nature, that it should not be flammable, it should not catch the fire. That means sustained at a higher temperature. Good flame retardant, they should not support the flame. Then they must have the dimensional stability. Once a certain shape that has been provided or certain dimensions that is given, they should retain that dimensions. Then good resistant to water vapor transmission, because in general case these insulations they are exposed to the atmosphere where it is raining, that will be there, and that is why this good resistance to water vapor transmission that is coming into the picture. Then economics, they should be cheap. So one by one we will talk, that is related to the asbestos, which is very common and at a lower temperature this can be used. Asbestos laminates and asbestos fibers. These asbestos fibers have good flexural and tensile strength, and it has the excellent water resistance. Then cellular glass, that is nothing but the inorganic glass containing microscopic hermetically sealed cells. Then cellular silica, that is formed silica is the main component of the rigid cellular silica. Then it has good compressive strength and good resistance to water and steam, acids, and it can withstand the severe thermal shocks also. Then diatomaceous earth, then glass fibers. These glass fibers, they are the most commonly used in the industries. That is, it's rolls made from the light bonded fine glass fibers that is available in the market. Rolls are available, and these rolls they are cut into the desired shape and provided the insulation over these pipes like this. Then blocks made of the bonded glass fibers, then filtered glass fiber blanket with various types of facings. Then lightly bonded glass fibers are soft, flexible, and has the little compressive resistance after application. They are generally used from 160 degrees Celsius to 315 degrees Celsius. Most temperature operating temperature range is in this range only. Then there is also the mineral wool. It can be used in molded blocks and loggings in mineral fibers blended with the semi-rigid blanket. Its temperature range is somewhat wider, that is 40 to 960 degrees Celsius. Then polystyrene, it is available in the blocks and pipes insulation. It has a moderate compressive strength and good tensile strength. Polystyrene has excellent resistance to water and steam. Polystyrene can be easily fitted It is flexible, clean, light in weight. Its use depends partly on the barriers of the effective services at lower temperature. Polystyrene is combustible. That is one of the limitations of the polystyrene, and that is why it is used at a lower temperature generally. Higher temperature it can catch fire, so this polystyrene is used at a lower temperature. That is your thermocol. Then the thermal conductivities of all these materials, that is very low. That is, the thermal conductivity is in the 0.675. Then the thermal conductivity of air is 0.022. Thermal conductivity of the air, that is 0.022. But these glass fibers, they are having the thermal conductivity around 0.6. So almost, if you will look, 0.6, 0.7, 0.4, glass fiber, that is 0.4 to 0.43, that we should know. Then for polystyrene, 0.4 to 0.45, this we should know. Generally these are the materials that is used. Then while designing, the different factors, they have to be taken into the account. Then selection and design of suitable insulation depending on the number of factors. The operating temperature is one of the important parameters. Then desired surface temperature. What must be the surface temperature, surrounding temperature? Then the maximum permissible heat loss per unit area, that is related to its thermal conductivity. Then economic thickness of insulation, economic aspects, that is to be taken into account. The situation of the insulation, how that insulation, whether it is going to the atmospheric exposure or going to expose it at a higher temperature, that all these different weather conditions, that is to be taken into account. Then application techniques to which insulation is subjected, how you are going to apply that. Out of this, maximum temperature, economic thickness, they are the important considerations. Then desirable properties for insulating materials, that is good load bearing properties and good tensile strength, that is required or expected. Then good resistance to vibrations and settling. That means in industry generally lot of vibrations because of the pump, compressors, wind, all these create the vibrations, and as a result they should get deformed in their shape. So to prevent that deformation in the shape, they should have the good vibrational resistance and they should not get settled. यानी ऊपर से पाइप को लगा हुआ है, बट ऊपर से इंसुलेशन निकल के वो नीचे में आ जाएगा, then the upper pipe that will get exposed. So to prevent or avoid this aspect, they should not get settled. Then good resistance to the moisture, then it should not be affected by the moist air, it should be incombustible, inflammable. Then desired chemical properties, it should be chemically stable within the temperature range of operation, then should be chemically inert, then should be colorless, non-toxic and non-irritant. That is one of the limitation, non-irritant also. It should have resistance against the rot, vermin, rodent and fungus formation. So biological, chemical and toxic, these three effects that is to be avoided. Now coming to the critical radius of the insulation. In general case, for a rectangular blocks, one can provide the layers of insulation one over the above and prevent the heat losses. But in case of a circular shape, that means a pipe or a sphere, circular shape, pipe or a sphere that is there, we can increase in the area as we are going to put the layers of insulation. So the area of this insulation that goes on increasing, the outer surface of the area that goes on increasing. So the area through which the heat transferred, that may increase, and that is why this critical radius of insulation that is coming into the picture. That is nothing but the common belief that the addition of insulating material on a surface always reduces the amount of heat flow to the ambient. ये कब होगा? जब flat surfaces है तब. But there are instances in which the addition of insulation to the outside surface of cylindrical and spherical wall does not reduces the heat loss. In fact, under certain conditions, it actually increases the heat load. It actually increases the heat loss up to a certain thickness of insulation. So, to establish this fact, let us consider an insulating layer in the form of hollow cylinder. What is going to happen in case of a hollow cylinder? So consider a consider this hollow cylinder or the sphere, the insulation that is provided and the metal wall that is available. So resistance of the insulation and resistance because of the convection that is taken into account. Here we are neglecting the resistance because of the metal wall and the inside convective resistance that is neglected. Inside convective resistance that is neglected. Second, the resistance because of this metal wall that is neglected. Because metals are good thermal metals have the good thermal conductivity, so they provide the good heat conduction, and as a result it is a sufficient amount of the heat that will be transferred through that, and as a result this first resistance of metal wall that is neglected. However, the resistance because of the insulation that is to be taken into account, and over that insulation the cladding that is provided. Cladding that is nothing but the aluminum foil which is surrounding that insulation. अंदर में इंसुलेशन है एंड उसके ऊपर एल्यूमिनियम की क्लैडिंग, एल्यूमिनियम की फॉइल लगाई है, so that insulation will maintain its shape, retain its shape. So from that cladding, how much amount of the heat that will be transferred to the atmosphere, that is taken into account. In a cylindrical pipe or a spherical shape, the additional insulation increases. Now, the temperature T1 to T infinity is the surrounding temperature. So, two resistances we have taken into account. One that is because of the insulation, and second that is because of the convection from the cladding to the surrounding. From the cladding to the surrounding. This is our convection. So, the resistance because of the insulation, this is we are doing the calculation for the cylinder. That is why ln R2 upon R1 upon 2 pi L into the K, and for convection H into A. A is the surface area, outer surface area of the cylinder. So outer surface area is having the radius R2, that is 2 pi R2 into the L, length of the cylinder, which is exposed. Surface area कौन सा exposed हो रहा है? That is the outer radius and the complete length of the cylinder, that is to be taken into account. So the critical radius of the insulation that will be there. So step by step we will consider the derivation associated with this now. So by looking at that figure and the same equation, Q which is equal to T1 minus T infinity upon R insulation plus R0, that is insulation plus resistance because of the convection. This R0, that is the resistance because of the convection, and R insulation, that is resistance because of the insulation. The other resistances, that is the metal wall resistance and the inside convective resistance, that is neglected. Now, from this first equation, R0, that is in the denominator, small r0, that means R0 is the outer radius or R2. So when the insulation is added, R0 or R2 will increase, and so will R insulation. As we are going to add the insulation, this radius of the insulation goes on increasing, and as a result R insulation, that is going to increase according to this formula, that is R0 is in the numerator. But however, R0, that is the convective resistance, will decrease as R0 increases because it is in the denominator. So it is possible that capital R0 may decrease faster than this resistance because of the insulation, causing an increase in the Q. एक increase हो रहा है और एक decrease होता है. तो as a result, there is a certain intermittent situation for this, and it is also a well-known fact that the Q would approach zero if an infinite amount of the insulation is added. This means that there must be the value of R0 for which Q is maximum. The value of radius R2 is known as the critical radius of the insulation and is denoted by RC. So it is seen that R0 or R2 is less than the critical radius of insulation and is added to the cylinder or pipe, the heat loss will increase and go through a maximum at the critical radius and then decreases. So this R0 less than RC, the Q that becomes increases and after that it decreases. So the concept of critical radius of insulation can be applied to advantages in different situations. For example, the pipeline carrying the steam must be lagged with the insulation so that R0, that is the outer radius, is always greater than the critical radius. In the case of electrical conductor chip, so the same equation we are going to write and we're going to calculate the critical radius of the insulation. For that, we are going to differentiate this dq upon dr0 and equate it to the 0. So differentiating this and equating it to the 0, you will get this equation, and this simplifies to R0, which is nothing but K upon H. K is the thermal conductivity and H is the heat transfer coefficient, convective heat transfer coefficient. So this is nothing but the critical radius of insulation. So another way of derivation that is also here, the same resistances R1, that is the resistance to the heat transfer due to the lagging or insulation, and the second that is the R2, that is the resistance due to the air film, that is nothing but the convective resistance. This R0 is nothing but R plus X. X is the thickness of insulation. X is the thickness of insulation and R is the inner radius of the insulation. Generally, the heat transfer coefficient from the air film to the surrounding is assumed to be the 10 watt per meter square Kelvin. So the total resistances are, that is the resistance due to the condensing steam and the metal wall, they are to be taken into account. So the same equation delta T upon the resistances, this is in terms of R and X. The previous we have talked in terms of the R I and RO. So differentiating this dq upon dx and equate it to the 0. So differentiating all these things and equate it to the 0, you will again get this same simplification, that is x, which is equal to k upon h, that is nothing but critical radius of the insulation, critical thickness of insulation. X is the thickness, k upon h minus r, k upon h minus r. This is what the thickness of insulation that is stopped, and k upon h, that is only the RC radius, critical radius. This is the thickness of insulation. This is for the cylinder. Now critical insulation thickness for the sphere. Again, there are the two resistances. One, that is because of the insulation, and second, that is because of the convection. When it's because of the insulation, it becomes, your formula is 1 upon 4 pi k into R2 minus R1 upon R1 R2. And for the convective heat transfer resistance, 1 upon HA, that is outer convective heat transfer resistance into the area, that is nothing but 4 pi R square. R2 square, that is the outer radius of the insulation, R2 or R0 or R plus X. So the rate of heat flow is a function of the surface area, that is nothing but your outer surface area. Therefore, the rate of heat flow is maximum at the actual thickness of insulation. So again, differentiating this dq upon dr and equate it to the 0. dq upon dr to equate it to the 0. So R2, that is coming as 2k upon H0. This is for the sphere. K upon H is for the cylinder, and for sphere it is 2k upon H. So for cylinder and for sphere, that is different. Now what must be the economic thickness of insulation? This is what the critical radius of the insulation we have talked. We have calculated the critical thickness above which the heat transfer coefficient that increases. Now coming to the economic thickness of insulation. This is based on the cost consideration, paise, rupees, cost value. It is the thickness of insulation at which the cost of insulation gives the best return on money. At this thickness, the sum of the cost of heat loss and the cost of insulation is minimum if the energy saving that is achieved. The thickness of insulation used is controlled by the density of material. As the density of the material increases, a lower thickness is required to provide the same thermal efficiency. Remember this in mind. Density also affects, because density that corresponds to the porosity, कितना voidage है उसमें, and वो voidage के ऊपर air, वो voidage is nothing but the air pockets. Air itself is having a lower thermal conductivity, 0.02, and this glass wool is having the thermal conductivity of the 0.6 watt per meter Kelvin. So the thickness of insulation used is controlled by the density of a material. As the density of material increases, the lower thickness is required to provide the same thermal efficiency. If the layer after layer of insulation is applied over the surface, then the heat saving occurs gradually. The lowest layer saves more heat than the upper one. Lower level will save the more heat than the subsequent layers. So, a limiting insulation layer balance the cost of heat saved and the cost of insulation itself. So now you have to optimize the cost of insulation and the cost of heat saved by adding the extra layer of the insulation. How much amount of the heat loss I am going to save? This is to be understood. A limiting insulation layer balances the cost of heat saved and the cost of insulation itself. यहां पे बैलेंस करने का है मेरे को, एक एक्स्ट्रा लेयर ऑफ इंसुलेशन में ऐड कर रहा हूं तो कितना अमाउंट ऑफ द हीट लॉस प्रिवेंट हो रहा है. So this particular critical layer is called as the optimum insulation thickness. So optimum thickness of insulation can be obtained by plotting a graph value of the heat loss and the cost of insulation versus insulation thickness. So value of the heat loss and the cost of insulation versus the insulation thickness. कितनी thickness चाहिए और वो cost क्या है. So one by one we will see here the different cost. C1 is the cost of steam in rupees per kg. We are assuming here that in a pipe the steam that is flowing and the steam that is getting condensed in the pipe, if the heat losses that is going to takes place, तो heat loss हो रही है steam से, तो क्या होगा, steam will get condensed. So on one side this cost of the steam which is getting condensed, that is to be compensated with the cost of applied insulation. So C1 is the cost of steam in rupees per kg. CS is the cost of condensing steam in rupees per second. So C1 cost of the steam, which is equal to the Q, which is nothing but M into lambda. M is the mass and lambda is the watt per kg. So C1 into M, which is nothing but C1 into Q upon lambda. This is watt per meter. It becomes equal to rupees per kg mass. Then CS is the cost of condensing steam in rupees per second. Then C2 the cost of lagging including the labor cost plus the cost of insulation. Then D1, that is the rate of depreciation, rho is the density, x is the thickness of lagging, length of the pipe, r is the radius of magnesia lagging, then Ts is the steam temperature, Ta is the ambient temperature, Tw is the wall temperature, K the thermal conductivity of the metal, H the heat transfer coefficient, lambda latent heat of vapor, M the rate of steam condensation, Ct is the total cost, and Q is the heat transfer area, watt per meter. So rate of steam condensation, that is nothing but M mass, which is equal to the Q upon lambda, Q which is equal to M lambda. From there this equation is coming. So CS is the cost of steam that is getting condensed. So M is the mass of or the rate of steam condensation, which is nothing but M into C1. So temperature difference into the C1 into 1 upon lambda ln of R plus X upon R. This is the value of Q, right? So temperature difference into the resistances because of the insulation and resistance because of the air fill. Two resistances that is taken into the account. Now the volume of lagging, which is V pi R2 square minus R1 square into the L. R1 and R2 into the total length. And this R2, that is nothing but R plus X. Sometimes this R2 is nothing but R0. RO, outer radius. So this volume that after simplification you will get, this volume is equal to pi x square plus 2 pi r into x. Then the weight of lagging, volume into the density, that is nothing but the weight. Then the cost of lagging including the labor, this much weight into this cost. C2 is the cost of lagging including the labor in the rupees per kg. So rupees per kg multiplied by the kg. Rupees per kg multiplied by the kg. Kg is nothing but the weight of the lagging. So the cost of lagging per year, that becomes equals to this thing into the D. D is nothing but the depreciation per year. So the cost of lagging per hour, 365 into the 24 hour per day multiplied by 3600 per second. That is cost of lagging per second. And this has to be equated with the total cost of steam condensation. Therefore, the total cost CT, which is nothing but the cost of condensing steam plus the cost of lagging. This is the first cost of the condensing steam, and this is nothing but the cost of the lagging. This is what? The cost of the lagging per second, and this is the cost of the condensing steam. This is the cost of a condensing steam. So at optimum thickness of the insulation, the total cost should be the minimum. So you have to differentiate this dCT, that is the total cost, with respect to the thickness of insulation and equate it to the 0. So you will get a total cost of the insulation versus the thickness. So initially, with the increase in the thickness, your cost decreases, and after this critical radius of the insulation, then it cost increases. Now we will solve one problem based on this. A steam pipe 10 cm ID and 11 cm OD is covered with an insulating material having the thermal conductivity K, which is equal to 1 watt per meter Kelvin. The steam temperature and the ambient temperatures are 200 degrees Celsius and 20 degrees Celsius respectively. If the consecutive heat transfer coefficient between the insulation surface and air is 8 watt per meter square Kelvin, find the critical radius of insulation. For this value of R0, calculate the heat loss per meter of the pipe and the outer surface temperature. Neglect the resistances of the pipe material. So RC, that is nothing but the critical radius of the insulation, which is equal to the K upon H. This is for the cylinder. So that becomes K upon H, which is coming as 12.5 centimeter. So heat losses per meter length, that is nothing but the temperature difference plus the two resistances for this cylinder, ln of R0 upon R1 upon 2 pi K plus the convective resistance. So that comes as the 620 watt per meter Kelvin. Now the value of outer radius and the critical radius shall yield the smaller value of Q upon L. So this Q upon L, which is nothing but T minus T infinity upon R0. So R0, the resistance because of the convection, that is calculated as simplification, you will get this thing, and R0, that is nothing but the convective coefficient. So that is coming at the 118.72 degrees Celsius. That is nothing but the outer surface temperature.